Hello everyone, on today's class we're going to start chapter 3, the longest chapter in the book. It's mainly focused on conduction. We're going to focus first on 1D, one-dimensional conduction. So if we start with a plain wall with a temperature 1 on the left side, which is the higher temperature, and T2 to the right, which is the lower temperature, and heat flowing from the left to the right. Heat always flows from the hot area to the cooler area. We're working with one dimension in the x direction only, and we'll assume the thickness to be L. Okay, and the assumptions that we're gonna have is 1, it's one-dimensional, 2, it's steady state, 3, there's no generation inside the wall, there's no heat being generated, and 4, if I remember correctly, it's constant K. Okay, so the K, the thermal conductivity, is not a function of temperature. Okay, it's constant. So to solve this problem here or example, we need to write down the thermal diffusion equation that we covered in the last class, which is second derivative of temperature over second derivative of x plus the second derivative of temperature plus second derivative of y plus q dot over k, which is our generation term, plus the storage term, which is density times Cp dt over d time. Okay, so our first assumption is it's one-dimensional. We're only working with x. Okay, so this will be 0 because we're not working with y. Steady state meaning there's no variation with time. That means there's no energy being stored. This term will be 0. No generation. This term will be 0, and constant K. Okay, we'll be left with second derivative of temperature divided by second derivative of x equals 0. Another way to rewrite this is the differential in terms of x of the differential of temperature over dx equals 0. So what we see here is basically a derivative of something gives you 0. In order for that to be true, this has to be a constant. This has to be a constant. Okay, so we can say that dt over dx has to equal a constant. We'll call that constant C1. If we're working our way backwards to find the function for this term here. Okay, so now we can integrate both sides to find that t as a function of x equals c1x plus c2. And that is the temperature distribution equation for the problem we have on the top. And we can see that it is a linear profile of temperature distribution, meaning that the temperature distribution in this wall has a linear profile. That's not really linear. Let me do it correctly. Has a linear profile. Okay. Now, since we know this, we can go ahead and state the boundary conditions needed to solve this equation. So we can start by saying first boundary condition is the temperature at x equals 0 equals T1, which is here. At x equals 0, temperature equals T1. Okay? So we can substitute x equals 0 into our temperature distribution. So temperature at x equals 0 equals C1. We'll substitute for x0, 0 plus C2. We'll change this to T1 because temperature at x equals 0 equals T1. Therefore, T1 equals C2. C2. Okay? Now, the second boundary condition is the temperature at x equals L equals T2. If you go back to the diagram, x equals L is at this point here. The temperature at that point is T2. Okay? You can go ahead and substitute this boundary condition in the original function that we found. Therefore, temperature at x equals L equals L C1 plus C2. We'll change this to T2. T2 equals LC1 plus C2 we found earlier to equal T1. Therefore, plus T1. Now, solving for C1, C1 equals T2 minus T1 over L. Now, since we have a value for C1 and a value for C2, we can substitute it into our temperature profile equation, which is Tx equals C1x plus C2. Therefore, Tx equals T2 minus T1 over L times x plus C2 is T1 plus T1. We can use that when solving for the heat transfer throughout the wall, which is conduction. The equation is negative Ka dt over dx, as we reviewed in chapter 1. Now dt, the derivative of the temperature profile in terms of dx of this equation here, will be T2 minus T1 over L, okay, plus 0. We can substitute it back to the heat transfer equation, and it will be negative Ka T2 minus T1 over L. I want to get rid of this negative here, and I can do that by switching these two terms. Therefore, Q equals Ka T1 minus T2 over L. That is the heat transfer through the plane wall. It can also be written in a different way, which can look like this. Q equals T1 minus T2 divided by L over Ka. And the reason the book writes it like that because it wants to compare it to Ohm's law, which is the change in voltage divided by resistance. Ohm's law. Okay. And from comparing it to Ohm's law, we can say that this term here is the thermal resistance, which is the conduction resistance, which is L over K A. While T1 minus T2, this term here, is the temperature gradient. Okay? Again, this can only apply if the four assumptions we assumed on top, which is one-dimensional, steady state, no generation, no heat being generated, and constant thermal conductivity. At that case only, you can compare the heat flow to the electrical flow and the thermal resistance to the electrical resistance. Again, what's driving the heat flow is the temperature change, the temperature gradient. Similar to Ohm's law, what's driving the current is electrical current is the change in voltage. Okay, now the smaller the thermal resistance is, the smaller the thermal resistance is, the higher the heat flow. So as you can see from the equation, in order to decrease the thermal resistance, you need to increase both the thermal conductivity and the area, which makes sense. If a wall's area is twice larger, the heat flow will be as twice more bigger. And if, for example, if you have a higher thermal conductivity, for example, copper, the heat flow will be higher than, for example, a lower thermal conductivity that's found in a concrete wall, for example. And the higher the L value, the higher the thermal resistance will be, meaning that, for example, therefore having a smaller heat flow. For example, if a concrete wall has a larger thickness, the heat flow will be smaller compared to when the wall has a small thickness, where the heat flow will increase. But to keep going, the same thing could apply to convection, heat flow, heat transfer, where Q equals HA times temperature of the surrounding minus the temperature of the surface minus the temperature of the surrounding. We can rearrange that to look like this: Ts minus T infinity, which is the temperature gradient, okay, the change in temperature, which is the driving force, divided by 1 over HA, which is the thermal resistance for convection. Just 1 over HA. Okay, to draw this as a circuit flow, this is your first temperature, T1. It goes through a resistance, thermal resistance, to reach T2. This is your direction of the heat flow, and this here is your conduction resistance. Okay, same thing could be applied to the convection heat transfer. That's the temperature of the surface. The convection air acts as a resistance, and that is your final temperature, which is the temperature of the surrounding, T infinity. Heat flows from the temperature of the surface to the surrounding, Q. and the resistance is convection resistance. Okay. This only applies for conduction if these four assumptions apply. For convection, there's no assumptions needed. This applies. This is true at all conditions. See you in the next class where we're going to do a couple of examples. See you then.